Hi everyone, so in this video we're going to talk a little bit more about just a few examples of exponential functions in the real world. Some growth, some decay. Let's start off with reviewing what we talked about last time about compound interest. So compound interest calculates how much interest is accumulated and how much you'll have in an account or even how much you might owe in debt based on the interest rate and all these things. So you fill in P, your principal amount, which in this case is 1,500, and then we multiply it by 1 plus the rate. That takes 100% of the original amount plus the additional amount that you gave for interest. In this case, it's 5%, so 0.05. And then, so that's what we'll fill in for R, is 0.05. And then typically we have to divide it by this n value, which is the number of times it's compounded per year, except for this one is only compounded yearly. So n would just be like a 1, which I don't really need to put that. And then it's 6 years, so I'll put in 6 for t. And again, you don't really need to put those 1s. This is really just like 1 plus 0.05, or you could even simplify that to 1.05 to the 6th power. Basically what this is doing is if I converted this to a percentage, it's taking 105% of that original amount every year for 6 years. So this formula, this compound interest formula, can be applied to other scenarios. If we start with a principal amount, it might not even be money. Maybe it's like the initial amount of bacteria in a petri dish, or the initial amount of people in a scenario. And then you basically just do 1 plus whatever the growth rate is, or sometimes even 1 minus the rate if it's decreasing in value. The n part doesn't really apply when we're talking about other scenarios, because we're not talking about how many times it's compounded, so you can kind of just ignore the n, and then you do to the t power, which is how many times are we repeating this process. So what that ends up looking like if we ditch the n is you end up with this model. You have a principal amount times 1 plus the rate, or 1 minus the rate, to the t power, where t is time, and then a is just the amount of whatevers that you have left. So let's see this in action. Imagine we want to buy a car for, I don't know, pick a number. Macy, how much you want to buy a car for?
5,500.
Oh my god. Oh, 5,500, okay. I was thinking 1,000. So imagine you buy a car for $5,500, and it's going to depreciate at 10%. So once you buy a car, it's going to be decreasing in value. It decreases a lot right at first, but once it's pretty old, it doesn't decrease all that much. So that's why it's an exponential decay function. So we can fill this in. We're going to do 5,500 times 1 plus or minus the rate to the t power. In this case, since it's depreciating or losing value, I'm actually going to subtract the rate rather than add it. If I turn this into a decimal, that would be 0.1. And so this is a model for this situation. This will give me the price of the car if I plug in various years. Notice that I could simplify this if I wanted to, so 1 minus 0.1 is actually 0.9 to the t power. And this is why it's decay. Because this number right here is less than 1, it's going to be exponential decay rather than exponential growth. So you do have to be careful. You don't want to just put 0.1 right here, you have to do 1 minus the rate. Don't just put the rate. Here's another example. Imagine we're just talking about mosquitoes. In this scenario, they're actually tripling every year. And we're going to start at 1999 in this scenario. So in 1999, when we start, there were 2,500 mosquitoes. That's like my principal amount. It's not money, but it's still the initial amount. I want to write a model for this situation. So I'm going to do the principal amount, which is 2,500. Typically we do 1 plus the rate or 1 minus the rate. However, this one didn't give me a rate. It actually just said tripled. So all that's happening here is we're doing 2,500 times 3, and then times 3 again, and times 3 again, over and over. And it's basically like taking 300% of the mosquitoes, which as a decimal is just 3, because we're tripling it. We're doing times 3 over and over. So this would be my model. The number of mosquitoes is equal to this, and I could plug in whatever I want for t. And t in this scenario is time after 1999. We may want to be specific about that. So if I want to know how many mosquitoes were at the beach in 2005, first of all, how many years after 1999 is that? That would be 6 years. And so I'll put in 6 for t, and so triple it 6 times, and let's see what that is. That's going to be a lot of mosquitoes. It's 1822500. So almost 2,000 mosquitoes. Hopefully that doesn't keep going up like that. Okay, so just be careful anytime it says like doubled or tripled or quadrupled. You just fill that number into the parentheses here as your base rather than doing 1 plus the rate or 1 minus the rate. And I think that's it.